So we're going to take a signal, x of t, and we're going to just put a condition on it that I'm sorry. It's just too ugly. We're going to just take a signal, and here's the thing. You can take any repeating signal and break it up into a series of an infinite series of a DC offset and cosine waves and sine waves. And you can get any signal to mathematically repeat forever if you integrate over that period. All right. So in practicality, things don't oscillate forever or for all time, but that's the assumption that we're going to make. And that's kind of the opposite of what we're doing with the Laplace transform, where we assume nothing is happening for before time equals 0, right? So what we have to do is, come up with the DC offset and the sines and the cosines to do that. And we'll do that mathematically and intuitively. But this content, it really builds upon phasors. And if you read I didn't assign it in the book, but the beginning of the chapter starts with phasors, right? And if we recall, a phasor is just a sine wave with an amplitude and phase that repeats forever. And if that's true, we can put it into a linear system, such as a low or a high pass filter, and we can find the magnitude and phase of the output, right? So far with our systems, right, we can put in an impulse and get the impulse response. We can put in a step and get the step. We can put in a ramp and put in the ramp. And one we never really talked about much, it was just one question on one homework assignment, is you can also input a sine wave, right? And that's really the Bode plot, where the x-axis is just a logarithmically progressing sine waves, and you're just plotting the magnitude and phase at each point. And so a phasor, right, a phasor is just one point on the Bode plot. And in this case, I've highlighted 1 kiloradian per second, right? And it gives me the magnitude and the phase at that point, which happens to be minus 3 dB and minus 45. All right. So we have been using Fourier analysis for quite some time. And really, that's when we said S equals J omega and said that these waveforms exist forever. We just switched to Fourier, even though we were using the Laplace transform to get the transfer function. All right. So now I just want to build upon your previous knowledge, right? And you'll realize that this isn't very different from something you've already done before, and that's finding the RMS of a signal, right? And here's the equation, when you find the RMS value, you take any repeating signal and you come up with kind of an average, right? But it's not just the average of the signal, we square the signal, right? Otherwise, sine waves, the average, with no DC offset, the average is 0. And what we're trying to do with root mean square is take a signal that repeats and see how much energy or ultimately power that signal will carry when you compare it to a DC signal, right? So if you have a root mean square of 0.7, that means that signal is carrying the equivalent energy or power of 0.707 of a DC signal, right? Because the RMS of a DC signal, of course, is the signal itself. All right. But let's just, what does that mean, right? Well, we're integrating the square. That's why we can get non-zero values, right? And we're integrating over the period. And if we were just integrating, right, it'd be called integration. But we're specifically integrating over the period. And then we're scaling by the inverse of the period. And so that right there means you are just taking an average. And so we're finding the average of a signal that's squared, right? And then taking the square root of it so that we can go back to, rather than volts squared or current or amps squared, we go back to volts or amps. So we can compare that voltage or current level to a DC one. All right. So really, all that equation is saying is that you're finding the average of something, right? Now, just one thing is that in 98 or your equivalent course, you probably learned a few tricks to making this integral easier. And really, those same tricks can be used in the when we're finding the Fourier coefficients. All right. Now, what are these Fourier coefficients? Well, there's all these sine and cosine waves, and we need to know the amplitude and the period or the frequency of each sine wave and cosine. Now, to be clear, we're taking a signal and breaking it up into an infinite series of sines and cosines plus a DC offset, right? This isn't the system, right? The system will operate on the signal, all right? So now really, we're gonna find this with a mathematical equation that acts like a prism, right? You shine light from the sun into a prism and you will see the reds, the yellows, the greens, and the blues. And so it spreads it out, right? And if you were to really zoom in on it, you could see terrestrially that there'd be certain frequencies missing because they've been absorbed by the atmosphere. And then when you're looking at a particular sun, right, there can be frequencies missing, right, depending on the heat of the object and what they're burning, if you will. All right. So, but rather than just kind of say, well, there is a color there, right, and it's so intense, you give you an intensity, we're going to take a signal and mathematically find this. All right. Now, if you you have a kit, let's see right. This has a spectrum analyzer on it. And what it'll do is if you send in a signal, these little peaks here are telling you that there's a sine wave at that frequency. There's a sine wave with a particular amplitude of that frequency and a sine wave of a particular frequency there. Now, yeah, there's noise because the spectrum analyzer doesn't know the fundamental frequency that you're looking at. And so, and then there's actual noise in the system, and it's a numerically calculated thing, right? And some, a lot of this goes into the graduate level, but really the spectrum analyzer on your kit, it's just like a prism. It doesn't give you the phase, but it will give you the magnitude. And then, yeah, so there's a frequency here at 20 megahertz and an amplitude of minus 20 dB. All right. So the Fourier coefficients are the amplitudes and periods of the sines and cosine waves that make up any signal. Now here, what they do is they combine the sine and the cosine, and then you attach a phase to it. So you're not going to see one for cosines and one for sines. You'll see magnitudes for a cosine with a phase. All right. So what is the first thing we need to do is find really the average, excuse me? We need to find the average of the signal, right? We're integrating over one period and scaling by a period. And notice how we're not squaring this and certainly not taking the square root, but it's almost the same thing, except it's not squared and no square root. And a lot of times this can be done, almost by eye, right? But if this was just a pure sine wave, there would be no DC average, or it would be equal to 0. All right. And we remember the RMS of a sine wave is not 0 because we've squared it. There's something there. All right. But, it's a very similar process. And you basically, though, when you see that signal, you have to identify the period. Otherwise, otherwise the analysis doesn't work, and it doesn't work as well. Now, how do we find the amplitudes for the cosine waves? Well, we integrate again over the period. We're still finding an average, although for it to work out, it's 2 divided by t, right? So we're still averaging, but rather than just averaging the signal or the signal squared, we're averaging the signal times a cosine. And there's something here is that n can equal 1, 2, 3 to infinity. And so the higher order of n, the higher the frequency. All right. And as you'll see, sometimes you can show that an equals 0 for everything, or that it's odd, or there's certain relationships. All right. But n is greater than 0. Then to find the amplitudes of the sine waves, right, you multiply it by a sine wave, and you just keep increasing n, 1, 2, 3. And you can use tricks and tips, and you can see that things sometimes cancel out. All right. But again, you're doing nothing but finding an average. All right. Now, this is just a simple process. Might not totally understand it yet, but that's okay. So you identify the fundamental frequency or period of the repeating signal. All right. So if it's a sine wave or a rectangle or, something arbitrary, you just have to see where it begins repeating again, right? And then what you can do is once you have that, you can intuitively or mathematically find the DC average using equation 1. All right. Then once you do that, you can estimate or intuitively or mathematically, right, the AN part, the AN constants. Then you do the BN. And then in the end, you sum everything together. So you can take that signal, right, and it's got a DC offset or it's 0. And then you just sum up all these cosines, n equaling 1, 2, 3, right? And they'll each have a coefficient that goes along with it, right? Same with the sine waves. Now, just some things. The fundamental frequency, omega naught, is 2 pi divided by t, right? So I could put omega naught here instead of 2 pi divided by t, but it seems to me to work out better when you leave it like that. All right. And if n equals 1, that's the fundamental frequency. And then the terminology is if n equals 2, that would be the second harmonic. If n equaled 3, that would be the third harmonic. All right. Now, just this is going to be a little bit of review, but it's kind of, you know, what does forever look like? Right? We talked about forever. So here's a low pass filter. And if we did the Bodie plot, and the way I like to, you know, when I know that the fundamental frequency, let's say, or the omega naught is 1 kiloradian per second, you know, and it's something simple like this. I go 2 orders of magnitude below and 2 more orders of magnitude above, and then it pops right out at omega naught when you click on the voltage in question. All right. So this filter, right, that's its transfer function. Tau is a millisecond, and 5 tau is 5 milliseconds, right? Now, what's going on here? Well, it's a little bit hard to see. You could find the period in the wavelength, but what I've done is input a 1 volt sine wave.
It's a low pass.
Yeah, it sure is. It sure is. Sorry, it startled me a bit. At 10 kilohertz, right? So the AC equals 1 gives me the Bodie plot with this, but now I'm running a transient and it's a sine wave and the input is 10 kilohertz, right? So 10 kilohertz sine wave would be here. That would give me 10 to the 20. Let's just 10 raised, oops. So I should get 100 millivolts out. Hopefully that's true. And I must have misread something earlier because that's not right. But what I wanted to show you is that notice how it doesn't start off like a regular sine wave. It starts here and then it decays down to the sine wave. And you can see how long does that kind of take? You know, 5 tau. All right. So the thing is for that low pass filter, if I apply a sine wave and then wait 5 tau, it'll appear like it's always been there. All right. Now you've probably done this a lot in labs, and you never would notice this because that's happening so quickly, right? Even as you're just turning on the oscilloscope, and as soon as you turn on the function generator and go over to look at the oscilloscope, you're already, it's already gone by. You'd have to actually put it on recording to capture that event where you turn it on and turn it off, and then you could see this, right? But this is like a Laplace way of looking at it, where you're getting the initial startup, and then here you're getting the Fourier, where it's like as if it's been going forever. So that's really what forever means. Let me just start deleting things. Okay. And so we're kind of using, our time domain and our frequency domain and our Bode and our Laplace kind of all together to figure that out, right? Now, before we do some examples on this, are there any questions? All right, so I spoke with Professor Morelos, who teaches one of the follow-on courses to 110, EE 160, which is communications, right? And 160 uses 110 and 112. And I had asked him, what's the most important thing that students need to learn from 110? And he's really like, find the fundamental frequency and the DC offset. And if you have that, then everything else should be easy. All right. So again, like I said before, we take any periodic signal and we can break it up to an infinite series of sines and cosines. But we got to find the initial frequency first. Then we determine if there's any non-zero DC average, right? So here we have V1 and it looks DC, except we're starting at 0 seconds. And this is the thing about LT Spice, is it's kind of like a Laplace finder, because even though you don't see it, the simulation assumes that it was 0 and then it jumped up to 1, right, at that time. All right. So here's the thing, how do you find the period of a DC signal, right? Because it kind of doesn't make any sense, right? There is no period, it's on forever. It was always on. But, oops, let's see if we can do that. So here's the equation, right, for the DC average, right? And in fact, if we just go through the math and we just kind of, I don't know what the period is, but I'm just going to pick one anyway, right? We get 1, right? And if it was a 1 volt DC, yeah, there's a offset of 1 volt DC. Now, what is omega naught? Well, it's 2 pi divided by the period, which is really, you can set it to be arbitrary, but really it's infinite, right? It was always on, it never repeats, or it repeats an infinite time, so omega naught is 0, right? A DC has 0 hertz, right? Then when we look at the, what are the cosines, right? So we take that 1, right? We integrate it times a cosine. We pick that period, and this turns into be 0, okay? And so you can see that, and it works out for the sines as well. Now, why did I go through all that? It's to show that, well, I have this new thing called the Fourier expansion or spectrum coefficients. Let me use it on a simple signal like a DC, and I should get a DC and all the constants of AN, which correspond to the cosines, and all the constants of BN, which correspond to the sines, should equal 0. And mathematically, that works out. All right. So now let's look at a periodic signal number 1. All right. So I look at that, and my AI tells me that's a sine wave, right? It's symmetric. Looks like it's symmetric about 0. And some people like to measure the period from peak to peak, or peak to peak here. That Scopy tool will sometimes it'll actually measure. It's actually measuring where does it cross a slope, but you can move almost something that looks just like this picture up and down to where it'll actually measure the frequency, and that way it stabilizes the signal. But we can see that the period is 1 second, right? And by I, the average is 0. So I've just taken, by I, I've got A naught. Now the rest of what remains to be seen is that, what are the rest of the coefficients? Now, again, just looking at it, because it starts at 0, this is a sine wave, and there looks to be only 1. So therefore, there can't be any cosines in there. So it's really just one sine wave. B1 happens to be that amplitude. So I put that there. And so it's just sine 2 pi t. All right. So that was really we found the Fourier expansion of a sine wave just for looking at it. But in a sense, by definition, if you only have one sine wave, if you only have one color of light and put it into a prism, you're only going to get one color of light, right? But again, by looking at it, and you can do this mathematically, you can find that the other coefficients, when you actually do the integration, go to 0. So the way I've drawn it, why can't it be a cosine? Is because the way I've drawn it, it starts at 0, right? And it's the waveform starts at 0, and at that's periodic signal too. All right, it crosses, and so the only function that'll fit that is a sine, right? Now, sure, could it be a cosine? with phase that adjusts the peak to where this turns out to be, matches it? Sure. But you're trying to do the simplest thing. And these equations have no phase in them. It isn't until you combine these two into one cosine wave with one magnitude, and then there will be a phase. Does that work, Riyadh? Okay, thank you. Oops, periodic signal 2. So I look at it, and now I'm going from 0 to 1. Oh, well, before, oops, I was going from -1 to 1, but now I'm going from 0 to 1. So it's clearly not symmetric, and so there's clearly a DC offset, right? So A0 cannot be 0. But then also looking at it, I see that I've nicely put some red arrows to identify the period as half a second, right? So the frequency is 2 hertz. All right. Now, again, I could numerically integrate that, and it'll give me the average, right? But just by eye, you can tell that it's a half, right? And actually, show you a little trick. So let's do a sine wave, amplitude of 1, keep it easy, and a frequency of 1, keeping it easy. Let's simulate that for 2 seconds. Here we go. Now, if I control left click here, right, it gives me the RMS and it gives me the average, which is pretty close to 0. But this is why I'm going to tell you why it's, now notice I did 2 periods, but I should get the same answer, right, if I actually did that numerical simulation over 1 period. Right? And again, that's microvolts compared to a volt. And that's, you can get that closer to 0 playing with some of the numerical settings. But watch what happens if so you would know that that's the period and you would integrate from 0 to 1. But what if we told the tool, right? So it went for 1.5. Well, just by looking at it, I can tell that, you know, I spend some time up, I spend some time down, I spend some time up, but there's no corresponding down. And now look, the average is actually, you know, around 200 millivolts. All right. And let's see if I can anyway, so by,
Professor?
yep, just let me finish one thought, right?
Sure.
So the thing is by integrating over the wrong area, I'm getting the wrong average. Okay. Yes, what is your question?
What percentage of, or what do you say is close enough? So like we're expecting the average there to be a smaller number, right? Um, what percentage, or like what number would be acceptable, basically, is what I'm asking.
I'm thinking.
Yeah, sure.
Yeah, because what I'm trying to give you is like a rule of thumb of like, I guess it depends what you're doing, right? If you're, let's say, you're numerically trying to find um, the coefficients, okay? So using LT spice, well then, using whatever, the standard SI prefixes, milli, things like that. You should have it within 2 digits of precision, right? But then on the exam, I'm trying to get you to show it to me in this intuitive way, and really, it's quite inaccurate, but I'm looking to make sure that the amplitude is like, is it positive or negative? And is it in the ballpark? Or is it actually so close to zero that it wouldn't, it's effectively zero, right? So I guess, unfortunately, there's a lot of conditions. But let's, what I'm going to do is add another signal. And maybe you can see it a little bit better. What I'm about to say. So I'm going to do a square wave, but it's going to be 0 to 1, very small rise times, 0.5 seconds on with a period of 1. Okay. And we'll run that. Oh, and I want to make sure that we'll run it for 1 period. All right. So now what I'm going to do, right, is remember multiplying a sine wave times your signal and finding the average will give you, and multiplying it by 2 will give you the right coefficient. So actually, if I just do V2 times V1, right, this is what gets integrated, this blue line, right? And so if I find the average of that, oops. Doesn't like it. But here's the thing. So on the exam, sometimes I'll give you, by multiplying these two together, you are trying to find B1 because the frequency of that square wave was 1 hertz this sine wave is 2 hertz, and you can clearly see that there is, a non-zero value, because I'll integrate this area. And let me get rid of V1, right? It's because it's squared, right? But you can see that there is a non-zero area here, right? What if that frequency was 2 hertz, right? Well, now you can see that it averages out to 0, right? Just by eye. What if it were 3 hertz? Well, I can see it goes up and comes down, and it looks to be canceled out. But then there's, an area that doesn't get canceled out. 4, everything cancels out. We're left with one area that's positive. All right. And yeah, if I put in a phase here, right, I could then turn it into a cosine wave and do the same thing. Okay. And so that kind of thing where you just see me like, all right, there's positive, and I could just estimate this as a triangle, right? That's really bothering me. Oops. I guess I'd have to do a behavior or voltage source, and then it would give me the average. I'll show you what I mean.
How did you get the average voltage?
Oh, sorry, it's just control left click. Okay. So that's just a rough kind of idea of what we're doing right now. How, doing it numerically, right? Now,
So basically,
actually,
sorry, can I ask a question real quick?
yeah, sorry, I didn't mean to cut you off.
Oh no, no problem. I was just asking. So basically, what you're trying to sum up is that we can do it mathematically, but we can also just most of the time we can just do it intuitively.
Oh, what's that term when you call it like a false choice, right? I think that's a false choice, is that I would rather you do it both ways, meaning, and it's also an interview tip. Let's say you get this question here and they just say, hey, can you tell me what the Fourier expansion is of this, right? And what I'm told is that they don't want you to like, all right, this is a square wave, okay, and then start plugging in the equation. They want to hear you talk about it and say, well, let's see, the period is 2 milliseconds. All right, so the fundamental frequency is 1/2 milliseconds. It seems to be going from -500 to 500 millivolts. So it seems to be symmetric, and it seems to be about on half the time. So I'm thinking that the DC average is going to be 0, right? And then so on. And so to me, it's like kind of like, I mean, do you ever get the feeling that sometimes your professors know the answer before they do the work? And it's not because they've done it ahead of time, which they have, but it's, you look at it and you try to break it into simple things, then you go do the math to find the correct answer, which at which point, you know, either they line up, right? Or they don't. And if they don't, then you know that something's wrong. Something definitely is wrong. Now, of course, you could have it wrong intuitively and wrong mathematically, but that the chances of that are smaller. Okay. So yeah, I would, in any problem, right? Yeah, why is that a low pass filter? Well, the resistor doesn't change with frequency. The capacitor is getting a smaller impedance with frequency. The voltage division tells me that it's getting, the magnitude goes down. Oh, low pass, right? Yeah, that's an interesting comment. Yeah, they hire for intuition, not computation. Because yeah, I mean, to actually go and calculate something, right? The machine can do that. What they need is somebody to tell the machine what to do, right? But so that's why I kind of stuttered on that question, because it's bigger. Yeah, maybe it's a bit bigger than that. So anyway, back to this. So looking at this, I can see that it's 2 milliseconds. And so omega naught is 1 kilopi radian per second, right? To keep it easier. And so, yeah, you can see the DC average is 0. Now, here's the thing. You can start intuitively trying to put in sines and cosines to see what's going to work. So I'm just going to put down one sine wave with an amplitude of 0.5 volts with a frequency of 2 and see how it fits in pretty well. So if I wanted to approximate this square wave, I could use a sine wave, right? Now, yeah, you can kind of, you see how this, there's this, it's underestimating the signal here and underestimating it here, overestimating, and so that there's errors, right? You need more sine waves to try to get closer to the signal, but you know, you got the first harmonic and the DC offset just for looking at it. Yeah. Yeah, Rad. You have to have intuition, but then you have to be able to back it up too, right? Also, you have to be able to explain how you work on a team. But you know, sometimes people make office hours and we go over, you know, how to prepare for a job interview. Okay. All right, here's another signal. Now I'm looking at it and it's going from 0 to 1. All right. And so the period is still about 2, but now it's no longer symmetric. And I can tell that if I you know, the average of this signal will be non-zero because it's not canceling out, right? So I just put another sine wave in there, but notice I've added 0.5, but then I still have the same magnitude, 0.5 times 1 kilopi times t, and I get my thing there. And the thing is that first harmonic will have the biggest amplitude. Okay. That'll be where most of the energy of the signal is, in the first harmonic. As you'll find out that as we start adding sines and cosines, the amplitudes of the higher frequency ones get smaller and smaller to where you can ignore it. Now, I've seen where people will take the first 9 or the first 13, but then when I've been doing something, it seems like you need 50 to actually get close. Anyway, I don't want to confuse you just yet. Confuse you later. So here we have a triangle wave, right? And the period, I believe, is 1 millisecond, right? And it's, again, it's going from minus 500 millivolts to 500 millivolts. And I've kind of drawn a line here. So, you know, here's a triangle of area that's positive. Here's a triangle of area that's negative. Well, they're going to cancel out, right? So A naught should be 0, which I must be right because I said that before. Now here's another one, right? I've shifted it up, but it's not a triangle the whole time. It's a triangle, then it goes to 0 for some time, then it's a triangle, and then it comes back down to 0 for some time. The yeah, it's 2 milliseconds long, right? But here's the thing, the period is this long, right? But the average, so it's not just the area divided by the time that it's on, it's the whole time of the period. Now, yeah, what you could do is, oh, you know, 1/2 the base times the height, right? And then scale in the proper period, right? And you'll just get, it's a half. Okay. Or I meant, oh, this is when it's on the whole time. There's no off time. In this case, it's the way I've drawn it, it's 0.25. All right. So okay, so now what we have is, this is a sine wave, right? And let's turn it back to 1 hertz. Keep it simple. Okay. So that's the sine wave. And then we square it, right? And this is the resulting signal. So whereas before, right, the sine wave average to 0, when we square it, right, I can see that even though it's a little bit different, you know, here I start at 0 and I'm going up. I'm back at 0 and I'm going up. So in fact, even though the original period was 1 second, this period is half a second. And yeah, when you square a sine wave, you double the frequency. And notice how the average would be non-zero. And so now the average is a half, and the RMS is 0.612. All right. But again, if you were trying to estimate it, right, you could say that's the period and do a triangle here. And the thing is the triangle, let's see if I can just. So what I'm trying to say is I'll estimate it with a triangle, is that I have a triangle here. I have a triangle here, right? And notice that the triangle is overestimating, so the area is positive, the error is positive. Here, the triangle is underestimating, so the error is negative. And yeah, you know, almost the way I've drawn it, those errors between the signal and my estimation of it just might even cancel out, right? Now, let's see so this is the signal we care about. So let's multiply it by a sine. Oops. Okay. So this is the B1 constant, right? And if I take the period of the new signal to be a half, right, it looks like I'm getting a Bn of 1 that's positive. Yeah, it's canceling out here, but I'm taking the period to be half a second, not no, actually. If I don't do this, if I keep increasing the frequency, okay. So now, now I've got it right. Okay, so for the first fundamental frequency of sine, right, You know, the shape is a bit weird, but if I'm integrating over that period, right, I'm getting, those areas are looking to cancel out, right? Some things I don't have off the top of my head. And so I'm going to leave it there to do the next example. Okay. So again, that's really what you'll be doing. And now if you look at the text, they're going to give you like 1,001 tips to setting for realizing that either ANs or BNs will be 0, right? If something is even or odd, right? If a function is even or odd, you know, it'll be composed of either sines or of cosines or sines. So right off the bat, if you can tell if it's even or odd, you can get rid of half the work. And here's the thing, is if it's even or odd, you can actually delay it to the point where it is even or odd. Okay. I have some old homeworks there. And actually, so now we're a bit running out of time really, but so here is like the hardcore mathematical way of doing it. And so in fact, right, in LT Spice, I have the B coefficients, right? I'm calculating everything, and you can see how I keep adding more and more sine waves, and it gets closer and closer to the square wave. Now, in fact, it never actually equals the original sine wave. There'll always be this ripple, but that's a subject for another day. All right. So before we head off to spring break, I just wanted to talk about, let's see. And it seems like a lot of people have headed off to spring break because half the class is missing. I truly encourage you to encourage your friends to come to class rather than listening to the videos later. It's just so that, you know, you're setting a time to think about 110. I'm not preaching to the choir because you're here, and I'm saying if you're talking to your friends, try to get them to come back. Okay. Assignments. So extra. All right. So extra credit midterm 1 resubmission. Again, I don't have to see that it's proved. You just have to prove that it's right. But what I'm finding is that sometimes the helpers aren't actually grading it properly, and that there's still things wrong, right? Now, I give you full credit for just doing it, but really make sure to go and read whatever comment you have. And then if you still don't get it, yeah, then come in. But yeah, only 11 folks have submitted that, and I would expect a lot more to have done that. And so, yeah, that's why I put a due date on that.
Understood. I see.
Okay, so sorry, I'm going to answer the first question here. So will the resubmission be commented on before the due date? I just started grading the ones that had come in. Here's the thing, you're going to get the full extra credit for turning in what you did. No, here's a hint. Please only turn in the ones that were wrong. Okay, that'll save me some time. All right, but I put a due date because I just had a feeling if I don't put a due date, other priorities will crop up, and you really want this done as soon as possible. But I mean, again, I'll tell you what's wrong, and then if it's still wrong, well, then you're gonna have to come see me, right? To figure out how to get it right. Does that answer your question, Jared? Okay, thanks. So, like I said, you'll get your full credit, right? But it might, it still might not be right. And we got to do that. Okay?
I have question. I saw
Yes,
that.
Fran.
Hi. I saw there's two midterm, which is the same on Canvas. When we click it, it's the same midterm practice.
Okay.
Yeah.
I'll see if I can, yes, shoot me an email.
Yeah, sure.
Okay? Yeah, you get some extra credit. The first one to turn that in.
All right. Have a good day, Professor David.
Okay. Okay. Listen, I had one more thing to say about the extra credit on the study midterm. So, so I know I said you could turn in the one you did, right? But really, you should take the one you did and fix it if there's anything wrong, because I'm finding in the study guides that there's, Bodie plots are done incorrectly, and so you really need to fix it, right? Now, sure, if I find an error, I'll still give you the full marks, right? But read the comments, right? Because I don't want you to say, oh, he gave me 50 points, it must be right. No, not necessarily, okay? And if your study guide has wrong information, it's going to be really tough, isn't it? All right, are there more videos? I'm laughing because there was a semester where I was experimenting with videos, well before the pandemic. Okay, was even on the horizon. And so there'll be today's lecture, and then there's 1, 2, 3 lectures before it. Oh, sorry. Once we're on, where are we? 17. Yeah, there's 3 lectures. Oh, that was from last year. So there's 4 lectures that exist already, right? I'd like to think I get better each time. So there'll actually be 5. And then and we're not really done either, right? We have more examples. That was for fall 19, right? So no, there's plenty. Yeah, so Justin, I'm sorry about it. If you have Wi-Fi. I'm just thinking that 40 people don't have Wi-Fi issues. So you can always download these videos, right? Even if you have bad internet, you can save it to an MPEG or something.
Yeah, I know, but sometimes I wish I just need to get toward it. Any
Yeah,
questions?
yeah. I mean, and yeah, for next semester, the university is telling me that any class above 50 will be online, right? But labs will be face-to-face, and classes smaller than that. So, yeah, we're gonna have to. I wish I could give you good internet. I'm sorry.
It's all right.
Okay.
All right. Have a
Take
good
care.
holiday, though.
All right, you too, everybody. Have a good spring break. You don't have to spend all your time on 110, but I would like you to spend a lot of it. Take care.